When we observe a jagged or irregular periodic signal, like a heartbeat monitor or a complex sound wave, it appears analytically inaccessible. Can any periodic function be represented as a sum of simple sine and cosine waves? This proposition redefined our approach to modeling physical systems. Today, we'll explore the mechanics of the Fourier series. Formally, a Fourier series is a mathematical method for expressing a complex, repeating function as an infinite sum of basic sines and cosines. The concept originated with Joseph Fourier in 1822. While attempting to model how heat conducts through a solid metal plate, he discovered that breaking the temperature distribution down into these basic wave components made otherwise impossible differential equations solvable. This technique provides a structured way to manage complexity. Instead of analyzing an unpredictable curve as a single entity, we treat it as a linear combination of well-defined standard parts. Because of this utility, Fourier's mathematical framework is embedded in several modern technologies. It governs thermodynamics and physical engines, compresses audio files into MP3s by isolating specific frequencies, and provides math for quantum mechanics. In modern mathematics, it provides a bridge between real and functional analysis, offering a rigorous framework for navigating function spaces. By translating complex signals into this clean mathematical vocabulary, we gain the precise control needed to engineer systems that interact with and analyze physical waves. We start on page 185 of Rudin with definition 8.9. This section formally defines a trigonometric polynomial as a finite sum of these basic wave components. Because sines and cosines repeat at fixed intervals, any function built from them is inherently periodic, typically defined over a standard repeating interval of 2 pi. Notice how equation 60 writes this out. By applying Euler's identity, the standard sines and cosines collapse into the more compact, complex exponential form. To actually utilize this sum, we need a mathematical method to isolate individual components from the whole. We achieve this through a property called orthogonality. Think of standard geometry, where x and y axes are perpendicular. In function space, different wave frequencies act as perpendicular axes. Multiply two different frequencies together and integrate over a full period. The positive and negative areas mirror each other, equaling exactly 0. This geometric fact leads directly to equation 62 on the following page, the formula for finding the exact Fourier coefficients, labeled C sub m. When we multiply the entire infinite series by the inverse of a specific frequency and integrate it, the orthogonality property ensures that every mismatched term goes to 0. This leaves only the one specific coefficient we want to measure. Orthogonality acts as a mathematical sieve. It allows us to extract the exact quantity of a single frequency component from a blended signal. Knowing how to isolate the coefficients brings us to Theorem 8.11, which analyzes the mean square approximation of the resulting series. Out of all possible trigonometric polynomials you could construct, the partial sums generated by Fourier coefficients provide the optimal approximation to the original function. Visualize this through vector space projection. Imagine our original function floating above a plane of trig polynomials. The Fourier sum drops straight down at a 90-degree angle. Any other arbitrary point on that plane increases the distance. The straight-down projection is the shortest path.
Rudin proves this by expanding the integral of the squared error. Its algebraic minimum aligns perfectly with the Fourier coefficients. This leads to Theorem 8.12, Bessel's inequality, establishing that the sum of these squared coefficients never exceeds the function's total squared value. Equation 74 reveals a corollary of this inequality. As we calculate coefficients for increasingly higher frequencies, the value of those coefficients must limit to 0. Physically, this means that as wave frequencies approach infinity, their amplitude contribution to the overall signal eventually vanishes. By minimizing the mean square error, the Fourier series is mathematically verified to be the most accurate structural fit for a given number of terms. We know the approximation is optimal, but to prove that this infinite sum actually converges precisely to the function at a specific point, we need a way to analyze the behavior of the entire sum.
The mathematical mechanism that makes this possible is the Dirichlet kernel, defined here in equation 77 and applied in the convolution integral of equation 78. Graphed, the Dirichlet kernel exhibits an oscillating shape with a tall peak. As terms approach infinity, the peak narrows and spikes upward, while ripples compress to zero. Like a spotlight, this kernel multiplies against the function, sampling its exact value at one target point. This brings us to Theorem 8.14. Provided the function satisfies specific smoothness conditions at a given point, the Fourier series will perfectly converge to the exact value of the function there. Rudin further explores this with the localization theorem, found on page 190. Unlike a power series, the convergence of a Fourier series at a specific point depends strictly on the function's behavior in a microscopic neighborhood around that point, even though the coefficients are derived from the entire wave. The Dirichlet kernel is the mechanical agent that forces an infinite sum of waves to strictly snap to the original function's true value. Theorem 8.15 confirms that continuous periodic functions can indeed be uniformly approximated by these trigonometric polynomials. But the culmination of this chapter is Theorem 8.16, Parseval's theorem. Parseval's theorem takes our previous bound from Bessel's inequality and upgrades it into a perfect, balanced equality. Looking at equation 85, we translate this math into physical reality. The total energy of the wave over time is exactly equal to the sum of the energies of its individual frequency components. The total energy in the time domain perfectly matches the frequency domain. We established orthogonality to isolate coefficients, proved that those coefficients create the optimal mean-square approximation, and verified how they converge to rebuild the original function. The Fourier series demonstrates that complex periodic phenomena are compositions of simpler waves, an insight central to both pure mathematics and applied science. If you enjoyed this detailed explanation of Rudin's principles of mathematical analysis, don't forget to like this video, subscribe to the channel, and turn on notifications for more chapter-by-chapter explanations of classic mathematics books. Share this video with your friends, and join us as we continue exploring higher mathematics together. Ultimately, the study of Fourier series suggests that complex physical signals can be mapped into the formal structures of mathematics. By establishing the conditions under which these series converge, we find that the behavior of a wave is recoverable from its component frequencies.